And thank you very much for inviting me to this occasion, which I'm very pleased to be here. I'm going to start by talking about a problem that's not my main subject, but it provides a bit of background or a bit of context. And this was a question that was asked by Babai and Shosh. And it's about product-free subsets of finite groups. So here's a very simple fact. This comes into Baylor's category of something that you can prove while cycling to your university, that if you take a finite abelian group, then it contains a sum-free subset. So that means a set in which you cannot find x, y, and z, such that x plus y equals z, of size, an absolute constant times the size of the group. And I can't remember what constant you can get. I think it's something like 3/7, but that's not very important. This comes from the fact that the worst, you just look at the worst group and it's some small cyclic group. And I think it might be C7, but I can't remember now. And so they asked, is that true for arbitrary finite groups? So is it true that for an arbitrary finite group you can find a product-free, so that means you can't find x, y equals z, a product-free subset of proportional size, so size at least Cn, where n is the size of the group and C is a positive absolute constant. My guess is that they expected that the answer was no. I'm not actually sure, but I mean, that was the natural thing to think, I think. And I answered this question, and in fact I showed that, well, I showed a sort of a general result connected with where what the thing that you really care about with the group, it turns out, is the dimension of its, or the smallest possible dimension of a non-trivial representation of the group. But a particular case that if you want to make that as big as possible, then the group to go for is SL2P, because that doesn't have, I mean, the sort of size of the smallest representations, their dimensions are proportional to the cube root of P, and that's about as big as it gets. And in that group, if I say that n is the size of the group, then it turns out that the largest product-free subset of that is a power of n that's strictly less than 1. So it's not just that you can't find a constant, you can't get anywhere near finding Cn points in a product-free subset. I won't say too much about that, but I will just say that the way it came out, it gave something stronger, but this is a very normal situation in a lot of contexts. And the stronger result is that if I take any three sets A, B, and C that are reasonably large, then I can find A in A and B in B and C in C, such that A times B equals C. So that's one direction that makes it slightly more general than the question that was originally asked. But the other thing to say, is that this is more what I want to focus on, is that what you get is that if you look at the set of all, well, actually I'm going to say it a slightly different way. If you pick a random element of A, so this A is picked randomly, and a random element of B, and I'm assuming that A and B are not too small, but yeah, they can be a lot smaller than a constant times the size of the group, then it turns out that the element AB is approximately uniformly distributed in the group. And what do I mean by approximately uniformly distributed? Well, I mean that for almost all G in G, so let's say for almost all G, the probability that AB equals G is approximately equal to 1 over the size of G, where G was SL2P. So the size of G is actually n, which I've written before. And if you want to be slightly more formal about it, what we get is if you look at the probability distribution, then it is close to the uniform distribution in the L2 norm. That turns out to be what comes out naturally from the argument. And because that's sort of saying that the variance is small. In fact, it's exactly saying that the variance is small. So it's saying that the probability is roughly equal to the average, except in a few places. Now, you can also get it follows straight away from this that if I actually take a random product A, B, C, so I'm randomly picking A from A, randomly picking B from B, randomly picking C from C, then that's approximately uniform in a stronger sense. I can replace that for almost every G by for every G. So that's saying that the distribution is approximately uniform in an L infinity sense rather than in a weaker L2 sense. So that's the background. So ABC, I'll write that because that's actually sort of the context that I wanted to have available. So approximately uniform in L infinity sense. So there's some epsilon greater than 0. I mean, there's a small epsilon such that the probability will always be between 1 minus epsilon times 1 over the size of G and 1 plus epsilon times.
How large are the sets?
Well, again, they can be n to the minus 8/9 times a large constant or something along those lines. And certainly if they're a small constant times the size of it, then you're in great shape. But, okay. So last summer, summer of 2014, I got an email from my collaborator on what I'm going to talk about, who's a theoretical computer scientist, Emanuele Viola. And he said a problem had come up in something he'd been working on in theoretical computer science, a sort of cryptography thing, which motivates what I'm about to talk about. It's a slightly quirky looking problem, so I think you have to know that there is a motivation for it that comes from theoretical computer science. Although, as I say, it is slightly quirky, but I think that the solution to the problem is quite nice and sort of interesting. So what I'm going to do is, I think, tell you as much about the maths as possible, and if I look at the clock and think I've got a bit of time to give some idea of how it relates to this theoretical computer science application, then I'll do that at the end. But I don't guarantee now that I'm going to do that at the end. I'll just see how it goes. So he asked the following question. Let's suppose you take two subsets. Let's make them dense subsets. So A and B, dense subsets of G squared. So for the time being, G, or in fact, probably all of this talk, G just means SL2P. I said in the title was highly non-abelian groups. Actually, I really should have said, what I'm actually going to talk about is just one family of highly non-abelian groups. It's just the best non-abelian family of groups, SL2P. But we think that most of what we're talking about can be generalized to other families of finite simple groups, particularly the ones of Lie type of small dimension and things like that. But we haven't actually fully sort of explored the extent to which that's the case. So I'll just stick with SL2P because that's where I feel on safest ground. Because for the cryptographic applications, you only needed it for an infinite family of groups. So if you had it for SL2P, that was fine. So I'm keeping you in suspense slightly. So what was the question about them? The question was, if I pick a random element A of A and a random element B of B, and I look at what we call the interleaved product, A1, B1, A2, B2, is that uniformly distributed or approximately uniformly distributed in G? So this is an element of G, but these are subsets of G squared. And a very important extra remark to make, this is definitely in the L infinity sense. If you just want it in the L2 sense, then it follows from the statement here that AB was approximately uniformly distributed in the L2 sense, because basically for an average A1 and B1, I've got a dense set of A2 and a dense set of B2. Their products are approximately uniformly distributed in, so a simple averaging argument gives you the whole thing that you want. So it's really, and it was important also for the cryptographic applications that it should be L infinity and not L2. So we want that for every element of G, the probability that that equals that element is about the same. So it's about 1 over the size of G. And, well, the answer turns out to be yes. Might as well say that straight away. But But before and I'm going to sort of try and give you the main ideas of the proof, and also talk about some generalizations. But before I do that, let me just give some sort of indication of why it's kind of anything sort of stronger than this won't be true. So this is sort of, in a way, the kind of a correct thing to ask. So supposing we just asked for...
Tim, could you just tell me what dense means in this context?
It just means has size at least the size of the group times an absolute constant. So at least sort of n over 1,000. But from the proof, we could actually, it could allow it to be quite a bit smaller than that. I think the proof will allow it to be, again, a power of n that's strictly less than 1. But all that mattered for the actual, yeah, we do. So if you want, I think it would be safe to say that if they have size n to the 99 over 100, you'll still be okay. So if you just looked for, if you had a subset B of G and A of G squared, and you asked, can you get A1, B, A2 to be approximately uniformly distributed in an L infinity sense? The answer is very easily seen to be no, because I just take B to be an arbitrary set of size a half of the group, and I'll take A to be all pairs A1, A2, such that the identity does not belong to A1, B, A2. And if B has size a half of the group, then for each A1, half the possible A2s will not give you the identity, and so you'll get a subset of A of size half of G squared. And so you can find a set of, just completely trivially, you can find a subset of half of G squared and a subset of half of the elements of G, such that the identity is not contained in, is not one of these elements. It's not contained in this sort of semi-interleaved product, or whatever you want to call it, of A and B. So you really need to go as far as A and B being dense subsets of G squared, both of them. Another small remark, I suppose, is that if A and B are Cartesian products, so if A is of the form A1 times A2 and B is of the form B1 times B2, then you're just picking A1 in A1, B1, and then it just follows straight away from the result that we had up there. So what's making it interesting is that you've got subsets of G squared that are very much not Cartesian products. They can be sort of high-rank subsets or something like that. Okay, so the proof proceeds via a bunch of reductions. So the first reduction is to define a graph. It's a bipartite graph, which I'll call gamma. And it's got two vertex sets which are both copies of G squared. So let me just... I'm writing that down because I think holding in one's head that it's a bipartite graph and each vertex set is also a sort of Cartesian product or something is just makes it ever so slightly complicated. Anyway, what is an edge? I'll say that x1, x2, so that'll be up here, is joined to y1, y2, if and only if x1, y1, x2, y2 is the identity in the group G. So I haven't mentioned the sets A and B at the moment. Now, supposing you want this statement to be true for all proportional sets A and B. Then in particular, so I take any particular A and B, one of the things I'm going to need is that the probability that A1, B1, A2, B2 is the identity should be roughly 1 over the size of the group. So if A is a subset of G squared and B is a subset of G squared, so A is some, I'm just thinking of it as vertex sets in this bipartite graph now. What do we need? We want that then number of edges from A to B should be around the total possible number of edges, which is the size of A times the size of B. So that's the total number of pairs A1, A2, B1, B2, with A1, A2 in A and B1, B2 in B. So with the total number of pairs multiplied by the probability that the interleaved product of a random pair is identity. So what we hope is that it'll be that divided by the size of G. And the point that I really care about is that we hope that that's true, for this conjecture to work, we hope that that's true not just for some specific A and B, but for all A and B. So for all reasonably large A and B. So for all, and actually let's think, what is the density of this graph? Well, if I just pick any old pair x1, x2 and any old pair y1, y2, the probability that this is the identity is obviously 1 over the size of G. So the density of the graph is 1 over the size of G. So what this is saying is that if I take any two reasonably large sets and look at the number of edges between them, it's saying that the density between A and B is roughly 1 over n. And this is a very well-known phenomenon in graph theory, in extremal graph theory. It brings us to the notion of a quasi-random graph. So I'll just talk a little bit about what a quasi-random graph is in case I know a lot of people here will know very well what they are. I'll just say very briefly for the benefit of people who aren't card-carrying combinatorialists. So a quasi-random graph is, the interesting thing about them is that they can be defined in all sorts of different ways. So one way is what I've just sketched here, which is, I'm particularly talking about quasi-random bipartite graphs, is that if you take the density between any two reasonably large subsets of edges should be roughly the same as the density of the entire graph. So we'll call that, that's sometimes called the discrepancy definition. Another one is that the number of 4 cycles, so if the density is delta, then if you look at what we call a 4-cycle density, which, so if you've got, say you've got m vertices and m vertices, and the number of, let's say, labeled 4 cycles starting down here, the sort of total number that you could possibly have is m, so m to the 4th. And then you want what you'd expect in a random case would be delta to the 4th, m to the 4th, roughly 4 cycles. So again, 4 cycles, I don't mean just 4 cycles, I mean labeled ones that start at the bottom and end up at the bottom. Or to put it another way, if you just pick a random 4 cycle, the probability that it'll be in the graph is delta to the 4. I think that's a nicer way of thinking about it. And that is trivially equivalent to saying that for almost any two vertices down here, if you look at the intersection of the neighborhoods of those vertices, that should have roughly the same size. So I'll just write intersections of neighborhoods, almost all roughly same size. If you take the sum of the squares of the sizes of the intersections of the neighborhoods over all pairs, it is just equal to the number of 4 cycles. And so that's why those two are saying the same thing. Okay. So what that suggests then is that we'd like to prove that this graph is quasi-random. So the nice thing about quasi-randomness is that we've got all these different conditions. So actually verifying directly that the number of edges between two arbitrary sets A and B is approximately some given number seems quite a difficult thing to do, but estimating the number of 4 cycles in the graph seems like a much easier thing to do. So let's think a little bit about 4 cycles in this graph. What does it actually mean? In fact, I'm not going to think about 4 cycles. I'm going to think about this last one, intersections of neighborhoods, I beg your pardon. So let's just take x1, x2, and y1, y2, and x1 dashed, x2 dashed. So what I'm asking you here is, what condition, if I fix x1, x2 and x1 dashed, x2 dashed, what condition does that impose on y1, y2 for it to be joined to both of these two? So we can write down a couple of equations. We get x1, y1, x2, y2 is the identity, and x1 dashed, y1 dashed, x2 dashed, y2, sorry, just y1, x2 dashed, y2 is the identity. From that we can deduce, sort of fun I think, doing simultaneous equations in some random sort of group. But anyway, so we get x1, y1, x2. We can eliminate y2. So we get x1 dashed, y1, x2 dashed. And we start to notice something kind of interesting, which is that x1 dashed to the minus 1, x1, y1 equals y1, x2 dashed, x2 to the minus 1, which is telling us that we were trying to say something about y1, y2, but we've ended up saying something about the relationship between x1 and, between this and this, which is that x1 dashed to the minus 1, x1 is actually conjugate to x2 dashed, x2 to the minus 1. And that's sort of extremely bad news. Why is that extremely bad news? What that's telling us is that if these two, or if that is not, let me just highlight it, if that is not conjugate to that, then there are actually no edges, or no, the intersections or neighborhoods is empty. You don't get any paths of length 2 from x1, x2 to x1 prime, x2 prime. But in a quasi-random graph, you wanted all the neighborhood intersections, or almost all of them, to be of roughly the same size. What we actually find is that if you don't get that conjugacy relation, there are nothing. And so therefore, if they are conjugate, you're going to get a much, much bigger number of y1, y2. Actually, it turns out, so once you've decided on what, so supposing they are conjugate, actually, let's just think about that for a second. So if those two are conjugate, then you certainly got some y1, and then by the orbit stabilizer theorem, it follows fairly quickly that, and also from the fact that in this particular group, almost all the conjugacy classes have roughly the same size, that you'll be able to perform this conjugation in roughly the same number of ways. So basically what the square of this graph looks like is, if they're not conjugate, if you don't have that conjugacy relation, you don't get any paths of length 2, and if they are, then you get roughly the same number of paths of length 2 in each case. So it looks as though this sort of idea of a proof has catastrophically failed, but there is a reason for its failure, and thanks to that reason, one can actually, there's something one can do about it. So the reason it's failed is I said that these were equivalent properties of quasi-random graphs, but I slightly lied to you. So they're equivalent, but there are certain constants, and when you go from one equivalence to another, those constants raise themselves to various powers. So you don't recover. You do actually between those, the second and third things, you get an exact equivalence right up to the precise constant. But between that and this discrepancy thing, which is very different looking, if you go from one to the other and then back again, you lose the constants that you've got in there. Raise themselves to a power. And what the effect of that on the theory is that quasi-randomness works for graphs as long as they're not too sparse. So once they get sufficiently sparse, raising to a power the density will then sort of make it so small that it'll just vanish or something like that, and things stop being true. And here, if we look at it, it is actually a pretty sparse graph. So it's got n squared vertices and n squared vertices, and density 1 over n. That's the square root of the number of vertices, or 1 over the square root. So that's why things have gone badly. But it turns out that, so it is actually not equivalent. This discrepancy thing is not equivalent to having 4 cycles. So the fact that the number of 4 cycles wasn't right doesn't tell us that the discrepancy is actually false. You can't translate that into a... So that's the thing that means that the news that at first looked bad is not actually quite as bad as it looks. And you can rescue it because it actually, if you use longer cycles, you can still get a criterion that implies this discrepancy bound. So in fact, it turns out that if we pass from 4 cycles to 8 cycles, then we're okay. So 8 cycles in the graph are the same as 4 cycles in the square of the graph, and or this is sort of some kind of weighted statement. But it turns out, as I said, as I was sort of trying to say before, the square of the graph is a weighted object. That's not how it's usually defined, but if I say that the square of the graph means that I weight an edge between this vertex and this vertex by the number of paths of length 2, then all those weights are either roughly the same non-zero number or 0. So if I divide everything by that non-zero number, then I can get it all to be 0 and 1, so I get something that looks like the square of the graph. So I find myself considering the graph, we find ourselves considering the graph where you join x1, x2 to x1 dash, x2 dash, if that is conjugate to that. Actually, we can make it look a little bit nicer if we sort of do something equivalent and think of it like that, as x1, x2 to the minus 1, x1 dash, x2 dash to the minus 1. That is a little transformation that you can do that keeps the problem the same. And then what you want is that x1, x2 to the minus 1 should be conjugate to x1 dashed, x2 dashed to the minus 1. That's the graph that we're considering. So we have an edge if that's true, and we don't have an edge if that's false. Now, if you look at that, you see that it's actually, sorry, I've written the wrong thing, and it's very important that it should not be that. So just, it's that x1 dash to the minus 1 conjugate to x2 dash to the minus 1. That's more like it. That is actually a Cayley graph. So we're saying that x1, x2, x1 dashed, x2 dashed to the minus 1, so that's just the operation in G squared, should belong to X, which is, by definition, the set of UV such that U is conjugate to V. So I've got some subset of G squared, and I'm using that as the generators for a Cayley graph. So this is just saying that x1 is obtained by multiplying x1 dashed by something, and x2 is obtained by multiplying x2 dashed by something, and those two somethings need to be conjugate to each other. So now what do we need this, what property do we need this Cayley graph to have? Well, we need it to be quasi-random. So we need that the number of 4 cycles in this Cayley graph should be roughly what you expect it to be. It should be roughly the sort of smallest it can possibly be. And that sort of comes to the same thing as saying that, again, that intersections of second neighborhoods should be roughly the same. And when you, again, sort of very simple things, what you actually turn out to want is that if I multiply 2 random ones of these together, it should be more or less uniformly distributed in the whole group. So I take U V, and U is conjugate to V, and I multiply it by, say, WX. It's not the same as this X, and those two should be conjugate. And then I want, so that gives me UW VX. I want this to be approximately uniformly distributed in an L infinity sense, in an L2 sense in G squared. So what I'm saying is, if I take something of this form, and all I know about it is that U is conjugate to V, and W is conjugate to X, but otherwise it's random, then I know basically nothing about this element at all. That is what the problem reduces down to in this sort of way. So what we could do then is just condition on UW equaling some particular value. So sort of, in fact, we could even just condition. I'm going to do something quite strong. I'll just condition on what U is and what W is. So what do I know about V and X? I just know what the conjugacy class of V is and the conjugacy class of X is. So I have two elements, V and X. I know what conjugacy classes they belong to, but otherwise I don't know anything about them, and I multiply them together. So they're two random elements. And what I would like is for that to be approximately uniformly distributed. So what that's saying is, if I take two conjugacy classes, C1 and C2, and multiply them together, when I say multiply them together, what I mean is I pick a random element of this and a random element of this and multiply them together and look at the resulting probability distribution. So I'm sort of convolving them. What I want is something that's close to the uniform distribution. And this turns out to bring us to an area that's been very studied by group theorists. So I want to mention a couple of papers. So one is, there's a famous paper by Leakage and Shalev, in which they talk about products of conjugacy classes. And they proved the rather remarkable result that in a finite simple group, if you take, let's just say it for one single conjugacy class, if you take a conjugacy class and you ask yourself the question, how many times do you need to multiply it by itself till you've got all the elements of the group? And the answer is the smallest it could possibly be. So it's the smallest it could possibly be is log of the size of the group divided by log of the size of the conjugacy class, and it's up to a constant correct. And there's a later paper by Shalev in which he shows something that for our purposes is sufficient, which is that if you take a typical element, so a typical conjugacy class, we can think of it like this: pick a random element of a finite simple group, another random element of a finite simple group, take their conjugacy classes and multiply those together. And that will be approximately uniformly distributed. We actually didn't know about that paper, so we did things in a completely direct way. And I would like to say just a little bit about how you can prove it directly. So what we're trying to do is show that for sort of typical conjugacy classes, so an atypical conjugacy class is, say, the conjugacy class of the identity. A slightly less atypical conjugacy class is the conjugacy class of something like 1, 1, 0, 1, the unipotent elements. Doesn't matter too much about that. So what we want to show is that if I take, so let's take I've got a U and I've got a V. I'll take a random conjugate of U and a random conjugate of V, and I'd like that to be approximately uniformly distributed. And this is what roughly what we did. We said we can think of G to the minus, well, we can write that as G U G to the minus 1h V. Sorry, yes, G to the minus 1h to the minus 1, and then just G to the minus 1. I've made it look slightly more complicated. But the pair G to the minus 1h, assuming that G and H are uniformly distributed, I mean the pair GH is uniformly distributed, then the pair G to the minus 1h is uniformly distributed. So what we're doing here is we're taking, U and V are fixed, so we're taking V, we're taking a random conjugate of V, then we're multiplying by U, and then taking a random conjugate of the result. Now why does that formulation help at all? Well, it turns out that in SL2P, things are quite nice for thinking about this sort of thing, in that there's a sort of almost one-to-one correspondence between the conjugacy class of a matrix and the trace of that matrix. It's not quite true always. For example, the trace of that is the same as the trace of the identity, but nearly always, if you know the trace, you know the conjugacy class. So we know that when we conjugate V by a random element, it's easy to prove that what you basically get is a random matrix with the same trace as V. So that bit here, we sort of get a matrix, we know the trace, and we know nothing else. It's sort of randomly distributed given the trace. Then we multiply by u, and that'll give us something with some other trace, and then we'll conjugate by a random g, which will then spread out into the conjugacy class corresponding to that trace. So what we actually need, because that'll do the spreading out once we've got the trace, what we need is that when we take a random matrix of a given trace and multiply by this fixed u, it will spread the trace around uniformly distributed. So we want the trace of that should be approximately uniformly distributed. So again, I'll just say quickly once again, this part here, I set a fixed v, so I'm just, by doing this, I'm getting a random element of the conjugacy class of v, and then I'm multiplying it by something. So what I want to say is if I take a conjugacy class and multiply it by some fixed matrix, then as long as the conjugacy class is not a silly one like the identity, the trace of a random element of this thing will be uniformly distributed in ZP approximately. So you find yourself, if you're doing that, considering the number of possible solutions to some equation. I mean, it'll work out as some simultaneous polynomial equations, because if U is some 2 by 2 matrix multiplied by something else about which you know the trace, and you want that thing, you want some sort of, you want the trace of that to equal actually some particular value, and you want to know what the probability is, well, that's the same as counting the number of solutions to a particular bunch of, well, actually it's a particular slightly complicated polynomial equation. And so it brings in arithmetic geometry. And just because that's the go-to area, that's where you have people who know how to count solutions to polynomial equations. And I won't say too much about that. I'll just say that the hardest case that came up, we actually did go as far as using Bayes' theorem, which sort of roughly says that if you've got an absolutely irreducible polynomial, then the number of solutions will be what it ought to be. It's sort of what it would be if it weren't a polynomial, but it were linear, up to a sort of small error, something like that. And that's exactly the sort of result we needed to finish off the argument. Okay, now I said I wanted to say something about generalizations. Actually, it's not clear in what sense what I'm about to say is a generalization. So here is the rough sense. The cryptographic motivation is generalized in a natural way, and that caused us eventually to think about this problem, which doesn't completely obviously generalize what I've just been talking about. So, and a special case of the problem we needed is the following. And I'll just give you the simplest case that we needed to consider. So supposing now we look at you'll have to bear with me just for a second. I know you can see what I'm doing. There's one situation where having pre-prepared slides is advantageous. Okay. Suppose you pick A, B, and C. Let's call this a, I don't know, I'll call it an oct. I'll say oct equals the set of these things, where A, B, and so these are octuples. So each octuple is an element of G to the 8, and these things here are elements of G. So I pick A, B, C, A dash, B dash, C dash. I form an octuple like this, and that's the set I'm interested in. So how many of them are there? Well, there are about n to the 6, because I've got a free choice of A, B, C, A dash, B dash, and C dash. And that determines the octuple, so it's exactly n to the 6. And for another application, what we needed was, so we needed a sort of, not actually octuples, but the sort of, this is dimension 3, we needed dimension 6 or something to, for this result, but if you can't do it for 3, you can't do it for 6. So what we needed was that if you choose sort of I'm going to call it let's make it omega 1, omega 2, omega 2, where each omega is one of these octuples. We choose those at random. Then for some, and we would like it to be the case that for some k that's small, and when I say small, I mean bounded above by an absolute constant, like sort of 100 or something. We really need it to be, what we'd like is that we would like omega 1, omega 2, up to omega to the k to be approximately uniform in g to the 8. So we've got to set aside g to the 6, and we take random elements of it, multiply them together. We want those to become approximately uniform very quickly. So g to the 6 up to g to the 8 doesn't look quite so interesting, but in the r-dimensional case, then the number of degrees of freedom you've got is 2r, and the size of the tuple is 2 to the r, and 2r is much smaller than 2 to the r. So if you're not impressed by this, make it a higher dimensional tuple. So the result is that, yes, we can indeed do this. We can get a constant k that depends only on the dimension, such that if you multiply just a few of them together, you multiply k of them together, chosen randomly, they'll be approximately uniformly distributed in the product group. Now, this actually follows from a much more general result that I think is sort of nicer, but this was the thing we needed. So it follows from the following principle. So this is just some subset of g to the 8. So let's look in general at, we'd like a condition on a subset, call it u of g to the r. We'd like some condition on u that will guarantee that if you multiply just a few random elements of u together, they'll be approximately uniformly distributed on g to the r. And we'd like that condition to apply when u is the set of octuples like this. And the condition that we fixed on was what we call sort of approximate pairwise independence. In fact, in this case, we get exact pairwise independence. So in what sense are these pairwise independent? They are that if you just look at any two coordinates, if I know what a, b, c dashed is, I have absolutely no idea what a, b dash c is. That's easy to, I won't bother proving it, but it's very, very simple. Well, a, b, c dashed, because I've got a free choice of c and c dashed, they're completely independent. So I've got a probability distribution when I pick a random element of oct, and it's pairwise independent. We don't actually need exact pairwise independence, we need a sufficiently approximately pairwise independence, which is actually important for the proof. What I haven't actually said what the statement is yet, but the statement is if you've got a subset of g to the r, where g is still SL2p, it's not something true for arbitrary groups, it's totally false for abelian groups, for example, then so if it's pairwise independent, that implies there exists M, depending on R only, such that a random product of M elements of U is approximately uniformly distributed in G to the R, where that approximation can be in the L infinity sense or whatever you like, strongest one you want. Now, a very small amount of thought leads one to realize that you only have to prove this when R is 3. And the rough reason for that is that if you can show that pairwise independence implies full independence after you've multiplied a few things together in G cubed, then what you can do is multiply a few things together in G cubed, and then just condition on the first coordinate, and then you've got, well, after you've done it in G to the R, you'll get something that's 3-wise independent, because if you just look at any 3 coordinates, you've got from pairwise to 3-wise. or pairwise to full, and therefore you've got three-wise independence. And then you just fix one coordinate and you're back to pairwise independence, and then you get a sort of induction argument and you're done. Slightly annoying thing about that is that it gives you a really rather unpleasant dependence on, a sort of exponential dependence of MR on R. And that's something that probably can be done better actually, but anyway, it turns out that the interesting case is, if you just want the abstract result, which was enough for our purposes, is to do it for R equals 3. I'm not going to say more about that argument, except to say that it actually used, in a slightly surprising way, the result that I've just talked about over here. So, well, not quite the result, but something that followed very simply from one of the main lemmas. I wanted to say something else. Actually, yeah, I think I'm torn between two things to talk about. So one is something else that is another result which I think we've pretty well got, although I feel slightly sort of uneasy about talking about it just because it's not totally written up in its final form. But perhaps I'll just mention briefly, one of the things that Liebeck and Shalev wanted their result for was that it enabled them to solve problems of the kind, can you express any element G of your group of choice as a product of elements that are words of a particular form? So maybe you want to write G as a product of elements of the form a squared b to the minus 1 a b or something like that. What you'd like is, in your group, not too many, you don't need too many of those to be multiplied together to give G. And a nice thing about these is that if you conjugate one of these, you'll get another one. So if I conjugate this by G, then I get another one of these, except I've just replaced A by A conjugated by G and B by B conjugated by G. So a conjugate of a word of a given form is a word of a given form. So that means the set of words of a given form is a normal subset. That's like a normal subgroup. It's just a set that's closed under conjugation. And so if you know that multiplying conjugacy classes together spreads out very quickly, then you know that multiplying elements of normal sets spreads out very quickly. So you know that words of a particular form spread out very quickly. So you can look at this as a sort of higher dimensional generalization of this sort of word idea. So that makes one think, what would be the kind of conjugacy statement from which such a thing would follow? And you find that the right thing to look at is what we call a multi-conjugacy class. So I am actually saying something a little about the sort of dodgy bit, or the bit that I feel is not quite finished. But a multi-conjugacy class in G to the R, so the multi-conjugacy class of x1, x2, up to xr. So the conjugacy class would just be, I conjugate that by something, I conjugate that by something, I conjugate that something. But the multi-conjugacy class, we insist that we conjugate everything by the same G. So there's gxg to the minus 1, or gx1 and gx2g to the minus 1, gxr, g to the minus 1. So if you do that to a word like that, you'll get another word like that. But if you do it with different g's and different coordinates, then it's no longer the case. So what you want to get a sort of rather general fact about words in powers of G is a result that says that multi-conjugacy classes mix rapidly when you multiply them together. And because of this pairwise independence thing, it turns out to be enough to show that bi-conjugacy classes mix rapidly, because if they mix rapidly, then you've got the pairwise independence condition, and then you can sort of take a few more products. And so anyway, I think that's sort of essentially done, but not in a form that's ready to make public, except in this limited sense of making public. So very quickly then, in the last 5 minutes, I think I owe you something about the reason for being remotely interested in these questions in the first place. It comes from a branch of theoretical computer science called communication complexity. And the rough idea of this is a slightly odd one, which is you have a whole bunch of people. They've all got and you've got, let's say you're trying to evaluate a function from x1 cross xn. Let's say there are n people, so x1 cross xn to, I don't know, 0, 1 or y or something like that. Let's make it 0, 1. And you've got n people, and each person takes whatever the object is. So this is going to be some object in here, which would be x1 up to xn. So person I takes xi and sticks xi on his or her forehead. You may have played a game called One Card Brag, so it's a little bit like that if you have. And can't see it, doesn't know what they've got on their own forehead, but can see what everybody else has got. And then between them, they have to work out what f of x1 up to xn is. And the rules are they're allowed to exchange bits of information, but they want to exchange as few bits as possible. So because everybody knows almost all the information, it should be sort of reasonably easy. So if you can prove that it's not easy, if you can prove sort of lower bounds on the number of bits that you need to exchange, that turns out to be quite important in theoretical computer science for various purposes, sort of a useful thing to be able to do. That's just, again, setting the context. So there are examples of that. I'm certainly not claiming we've got the first example of such lower bounds, because that's not the case. But we've got examples with certain properties that have slightly more subtle cryptographic consequences that I actually don't fully understand myself. Some things called leakage resilient circuits. But let me just say what communication complexity itself has to do with our results. So we could imagine that each xi is a 2x2 matrix that lives in SL2P. So you've got, try this game with your friends if you like. You each take a 2x2 matrix in SL2P, and let's say 3 people, to make it simple. You can see the other 2 people's matrices, and you'd like to exchange as few bits as possible and work out what the product, work out whether, let's stick actually with 2 people's, because then it'll relate it to the first thing. So actually, sorry, what I mean is you've got 2 matrices on your forehead. You have 2 matrices, and the other person has 2 matrices, and you'd like to work out whether A1, B1, A2, B2, these are matrices, not matrix elements. So somebody has promised you before the game starts that either it will be the identity or it will be some other 2x2 matrix in SL2P. But they haven't told you anything else. And your job is to exchange as few bits as possible and work out which is which. Well, there's an obvious thing you could do. I could just tell you exactly what my 2 matrices are. And that gives you a trivial bound. And what we'd like to say is sort of roughly logarithmic in P. Now, what it turns out, each time I exchange a bit, each time I tell you a bit, I'm telling you something about A1, A2. And each time you tell me a bit, you're telling me something about B1, B2. And so what that sort of boils down to, it, when one thinks about it, is after we've exchanged a few bits in this protocol, what we know is, roughly speaking, that we've restricted ourselves to some, if we've only exchanged a few bits, some reasonably large vertex sets in that bipartite graph I told you about before. And because the 2 graphs that you get from A1, B1, A2, B2 is the identity, and A1, B2, A2, B2 is G, are both pretty quasi-random in the sense of having low discrepancy, that information is of absolutely no help in distinguishing between the 2 graphs. So what it really boils down to is until your 2 people have exchanged really a lot of bits, not only can they not tell whether it's the identity or G, they can't even guess with probability better than 51%, which is the right answer. And the sort of thing I was talking about here arises when you have multi-party problems. So you've got, it actually generalizes in 2 ways. So you've got more people and more matrices. If you've got more matrices, then you just go my first matrix, your first matrix, round and around the circle, then my second matrix going around the circle, my third matrix. And what we want is that the number of times you have to go around the circle isn't too big before you just can't say anything at all. And that's what this, where is it, this M, it was the thing that we were trying to make small. Okay, I think I've said enough now. I've reached the official end of the time, so I'll stop there.
Okay. Perfect timing. So, are there questions?
How large is your MR?
Well, it's exponential in R.
What do you expect to be best?
I would guess it would be a polynomial in R. I mean, there's this argument I gave, it's rather simple, but at the same time slightly lazy argument where you do an induction. And I sort of feel that I don't see a way of doing it. One really ought to try to do an induction sort of where you split it into two sets of half the size or something like that, instead of one set of size 1 and one set of size k minus 1. But as I said, if you're just taking root 1 to the statement that was needed about leakage resilient circuits, we only needed it for a fixed k like 6, and so yeah.
You don't expect it to be linear.
I don't know. I don't think it, I wouldn't rule that out. I feel, yeah, might be, might not be.
More questions? Yeah.
So for 3% communication complexity, you get better lower bounds than what's known by some other species function?
No, it's not like that. I think what's sort of interesting about it was that it's sort of scaled up with the size of the group. So you don't have to go around the circle very many times, and then as the group gets bigger, the bound goes up. So I think previous examples based on groups reduced to some other example, which if you only went around 3 times was sort of basically a constant. So I'm not claiming any new lower bounds in communication complexity. They did solve an unsolved problem, though, other than the sort of question that we started with, which is something to do with leakage resilient circuits. Now, leakage resilient circuit is something like a circuit that will calculate a given Boolean function and won't tell anybody, it won't tell an adversary any information if they only look at certain aspects of the circuit and that sort of thing. So it's a sort of cryptographic notion, which I have to admit that I don't fully understand. I was just kind of took a slightly pure mathematical attitude to it and trusted that this application was there and enjoyed the problem. So.
Okay, still more questions? I see none, so let's thank him again.